we can make reference to the energy of what's happening within the reaction, so we can look at exo versus endo. What's happening in A? Endo. What's happening in B? Exo. How do you know endo versus exo? That doesn't look like an E at all. Your product energy is lower than your reactant energy, so you're looking at an exo in that situation. C, endo, D, exo. What could we say about all of these reactions? What do they all have in common? I would agree with all reactions. I want a little bit more information than that. You got the right information.
Yeah, they all require.
So they're all going to require some energy to get over, so we could say that's the same. I don't know how I'm going to write this. Same. They all have some activation energy.
All their graphs are on the same slide.
That's true. We could look at it as a reactant going to a product, meaning that we are a one-step reaction. All of these are one-step reactions, okay? Because there is no intermediate. So we could also add that, no intermediate. I don't want to classify that yet, but we will be talking about SN2 and SN1. You can kind of cheat because you already had lab. What else could we look at? What else comes off of an energy diagram? Kinetics.
Yeah.
How fast the reactions occurred. So we could compare A to B. What would we expect for the speed of those reactions? The rate should be the same. Why should it be the same?
Because they both have the same energy.
They both have the same activation energy. Okay, how about between C and D?
Same thing.
Same deal. We would expect the same rate for those.
Are you sure they're the same?
Close enough. Why, would you like to suggest that there's a difference?
I don't know. You're arguing about this. You're like, I don't think. I was like, I don't know.
It looks like D could be
It
lower
looks like
activation
D could
energy.
be a
D could be a little bit lower than C. Yeah, it's beside the point. It's close enough. What's happening between A and C? C should be faster than A because
Lower energy activation.
its activation energy is lower. How about D versus B?
Same.
Same deal, D should be faster. Okay? So you kind of get the idea on what you should be interpreting off of these. Can we add some more stuff to it? Say which one has a negative delta G? The exothermic reactions are going to have the negative delta G's, a spontaneous reaction. So we'd be looking at B and D. So we can phrase this information in a variety of different ways. We could say exo, or we could say negative delta G's. What about non-spontaneous reactions? Which of these are non-spontaneous?
A and C.
A and C, which is in reference to it being an endothermic reaction or a delta G that is positive. We could also go in and look at the equilibrium constants. Which equilibrium, or which of these reactions is going to have an equilibrium constant that is bigger than 1? B and D, because products are favored. Lower energy than our reactants. Okay, so there's a variety of ways that we can put that information out there and ask those same questions and get back to the same general ideas as far as interpreting the graphs. Okay, so we went through and talked about each of those in kind of a slow progression, or what I may have considered slow, maybe it wasn't slow, on Monday, and we've just kind of put it all together into one big kind of summary slide for everything. How much this information needs to be on your quiz to actually get full credit? No, I don't know. I haven't figured it out yet. Okay. As long as there's a few of those correct statements in there, we'll probably just accept it and give you full credit for the quiz. Okay. Remember, the idea on the quizzes is not to be a punishment, but to get you kind of thinking about what's happening within it and kind of go over what's going along with those reactions. Okay. Questions about Chapter 6 and our energies? Okay. Again, when it comes to Chapter 6, doing practice problems, I finally was able to get Sapling homework questions up, so there is now a homework 15 that is available. I do apologize for the delay on that, My internet has apparently decided to fail, so I don't have any ability to do anything at home. So I just put that together this morning. It's a total of 6 questions, I think. You'll go over some alkyl halide stuff, and then most of it is going over the energy diagrams, okay, doing some kind of interpretation off of those. Okay? So after the end of today, you should be able to do homework 15 without a problem. You should be able to do most of 16 and probably parts of 17 after today. Okay? The rest of the homework is then going to push into elimination reactions, which we'll cover next week, okay? Probably Wednesday. Actually, before we step in a little bit further with our alkyl halides, there have been some questions about preparing for the final. The final is a standardized test that we are working towards preparing you for by going over the general information. I do try and design the questions to match what you would expect to see on the final, and we set up the format very similarly as well. If you want the extra practice on what's happening with questions for your final, there is an ACS study guide that you can purchase from the ACS people for $20, and it's got all the questions for an entire year's worth of chemistry or organic chemistry. So you can only answer certain sections that they provide. If you don't want to purchase it, that's fine. I've got a copy that I will try and remember to always drag around with me, so that while in office hours you can borrow that from me. Also in the tutoring center, there's also another guide in there as well. Okay, so you can use that one. You don't have to purchase it as long as you're using it in the tutoring center. So I would highly recommend that to help for the ACS test. Like I said, what we're covering does reflect that material, but ultimately the questions that are getting asked are coming from their style and their points of view. Okay? Chapter 7, we're looking at alkyl halides. Okay, so this is the first time we're really advancing forward with legitimate chemistry. With our alkanes, we pretty much said we didn't have any real reactivity available to us. That's a pretty big exception to that, which we'll talk about in a couple weeks when we move into chapter 15, our radical reactions. Okay, but in general, when we look at our alkanes, the intermolecular forces, we've got carbon and hydrogen bonds and carbon-carbon bonds, which are covalent bonds, which lends to which type of force? London dispersion forces, so we get very weak forces, which means when we look at melting points and boiling points, we get very low melting points and boiling points, because it's not very difficult to break those molecules away from each other. And then this also pushes into our reactivity. Without those polarity, without a positive and a negative charge within the molecule, we don't really see those molecules reacting with other things. There's no reason for them to react, okay, because they're nice and neutral already. Okay, what happens if we push up to the alkyl halides, however? So in the case of an alkyl halide, we're talking about alkyl, meaning any kind of carbon-containing structure. So I guess we can tag that on here. So we've got some kind of carbon structure, and we're usually looking at these as sp3 carbons. We won't attach it to, say, carbonyl carbons or anything like that, because that's going to change the reactivity too much. Okay, so what we're looking at is just pretty much a singly bonded carbon with a bunch of whatever else coming off of that carbon. Sometimes you'll see double bonds show up. Again, we're just saying anything with really carbon in it. And then we're looking at your halogens, or your halides. Why do we refer to it as halides and not halogens? Because they're ionized. Okay? Halides typically carry that negative charge. We're not looking at them in their neutral state per se. They're coming in with kind of a pseudo-negative charge. So we're looking at chlorine, well, sorry, I guess I should start appropriately. Fluorine, chlorine, bromine, and iodine. So anytime we see any of those elements attached to a carbon, our first pass at what that functional group is going to be an alkyl halide. Okay? We got a couple example structures up there. We'll talk about those in a little bit. What would we expect for our intermolecular forces? Why dipole-dipole? Why is there a charge? Someone was mentioning it. There's a difference in electronegativity. Our halogens are very electronegative. Carbon is not. The halogens withdraw that electron density in the bond. They become partially negative. The carbon, having lost that electron density, becomes partially positive. Okay? That generates a polar covalent bond, which then gives us a dipole. We then have the ability for dipole-dipole forces. Right? As far as our melting points and boiling points go, what would that do to our melting point and boiling point relative to an alkane? It should increase, because we now have a stronger intermolecular force between those molecules. What's going to happen to the reactivity? It's now going to become more reactive. What is that more reactive? Okay, so let's actually pick a simplified structure. Let's just take a carbon. We'll bound it to a halogen, the lone pairs. What reactivity do we have available to us? Okay, well, we said our primary issue was that that bond spends most of its time with the chlorine. So what charge does the chlorine build? Becomes partially negative. What charge does our carbon build? Partial positive. Okay. What kind of species are partially positive? So we've got our 6 definitions for reactivity, and we could start with Lewis. Our Lewis acids are partially positive, so for sure we would expect this to act as a Lewis acid. Should it be a Bronsted acid or an electrophile? Why should it be an electrophile? The positively charged atom is not hydrogen. So we're looking at that carbon acting as an electrophile. Okay? So that's one source of reactivity. So that's our positive end. We still have that negative end, so let's address that. Okay? If we have a negative, what could it potentially act as? A nucleophile. For it to act as a nucleophile, so this is where we have to be careful with our definitions, that atom must share its electrons with something else. Where are the electrons on that chlorine? In the lone pairs are going to be our highest energy electrons that could potentially react. Can that chlorine take one of those lone pairs and share it with another atom? Why not?
And you would add another.
It would create
Add
a charge.
another,
From the other one, from the other atom. Wouldn't it be?
create another bond. What's the issue with making another bond on our halogens?
There's no bond available, there's no one.
Can't bond anymore. You're-
Halogens can only form one bond. Okay? So yes, that halogen may be partially negative. So that puts us in the position of saying maybe it's a Lewis base, but can it share those electrons? No. Okay? So just because it has that charge does not mean it will act as one of our definitions. We have to evaluate, can those electrons actually be shared? And in this case, we can't share those electrons because our halogen has already satisfied its one bond. So what does that mean as far as the reactivity of our alkyl halides? We won't have a Lewis base, but we do still have a Lewis acid in the presence of our carbon. Okay? So if we go through and evaluate, we've got our dipole-dipole force, we've got our higher melting points and boiling points, and we would expect our carbon to be electrophilic. We can bring electron density in to share with that carbon, okay? Because that carbon is now partially positive charge. Okay? So any ideas why we might be working through our functional groups in this order, starting with our alkanes, then moving to our alkyl halides?
Order of increasing reactivity.
We're looking at an order of increasing reactivity. Okay? We don't jump straight to, say, carboxylic acids, because if you look at a carboxylic acid, it's got an electrophilic carbon, an acidic hydrogen, a nucleophilic oxygen, and a basic oxygen. Okay? That's a lot of different reactivity to consider all in one step. Okay? So that's why we're trying to slowly work our way through, and as we add different functional groups, we're going to start to have to evaluate each of those atoms and decide, does that have an increased reactivity or not? If it does, we need to then address that reactivity. Okay? Interesting alkyl halides that are floating around. We've got chlorofluorocarbons. What were our chlorofluorocarbons used for? Aerosols, CFCs. Okay? They've been kind of removed or become controlled substances. Why? They damage the ozone. So what happens is those have relatively less or light density or small density, float up into our atmosphere. They react with the atmospheric gases and UV radiation and ends up destroying our ozone. So it's a bit problematic, so we decided to ban the use of those. Turns out we didn't do a very good job, but that's beside the point. So CFCs is typically how they're referred to because chloro for C, F for fluoro, C for carbon, our chlorofluorocarbons. DDT is another common molecule that was used. What's the issue with DDT? It's a pesticide. It's an awesome pesticide. It does a really good job killing insects. What's the other issue with it? It builds up in fatty cells, and one of the primary reasons why we got rid of it is it kills our national bird. Okay? It weakens the eggshells to the point that when the bird sits on them to incubate the eggs, they break the egg. That's kind of problematic if we want eagles to continue to live. Okay? If we keep destroying their offspring. So that ended up getting banned because of those secondary effects. Okay? With that structure, you'll notice that we're trying to show a variety of different things here. If you look really, really carefully at that structure, you might see some kind of dotted lines. Okay. What's going on with those dotted lines? What we're trying to show is resonance there. If we go through and again evaluate our atoms, we've got a carbon at each of those little nodes. How many bonds are shown to that carbon? So let's just erase all of those.
2 or 3.
We've got 1 to the next carbon, 1 to the other carbon, and 1 out to a hydrogen. That's only 3 bonds. So we might say, oh, there's an implied hydrogen. We've specified the hydrogens already. So we can't imply a hydrogen because it's already drawn on there. So what does that mean is missing? There's a double bond. In this format of drawing, we can't draw double bonds very easily. So what ends up happening is we can imply multiple bonds as long as we don't imply hydrogens or charges. Okay? So what we're actually showing in the structure of DDT, let's just take one of those branches. We've got 6 carbons, and that goes off to our another carbon, chlorines. Let's add in our other chlorine out here. What we're saying is we actually have double bonds within that structure. If we go all the way back to everybody's favorite 9-letter word, we have resonance within this structure. Because those double bonds can exist in between every single one of the carbons equally, what we can do is instead of drawing them all out, we can draw it as a hybrid structure. And we're saying that the double bonds can actually exist here, 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 and here, which really starts to look like a ring, a circle within it. Okay, why do we go to a circle and not draw inscribed hexagon? Well, my inscribed hexagon looks pretty ugly. Okay? That's probably the primary reason, and it takes too much time. So what do we end up doing instead? We just draw a circle saying, yeah, the electrons are somewhere in there. Okay? We can do that with pi bonds. We can't really get away with that when we look at single bonds, because we have to specify our sigma bonds very cleanly. Okay? One of the other common alkyl halides is tetrafluoroethylene. Depending on time, we might actually talk about this type of reaction. What we're looking at here is what's known as a polymerization. So we're taking multiple of that tetrafluoroethylene and we react it several times out. We react it so much that what we end up getting is a very long carbon chain that just repeats. Okay? Because we're lazy and we don't want to show 50,000 carbons all linked to each other, we just put parentheses and say, oh, copy, paste, copy, paste. Okay? And what we're really specifying with that lower right-hand corner, there's an N there. Sometimes, if I wrote 8, what does that mean? There's 8 of those repeating outwards. Okay? If I wrote 400, 400 of them repeating outwards. Okay? So it's just a shorthand for that. Okay? So if we polymerize tetrafluoroethylene, we end up with polytetrafluoroethylene, also known as Teflon. It's our nonstick coating. It is actually due to this compound. Okay? Or one of our nonstick coatings. Okay, so it's kind of a neat structure in that case. What ends up changing? Well, we were talking about higher melting points and boiling points. Typically, our alkyl halides might be in the liquid phase. When we move to Teflon, what happens? It's a solid. But it's still a fluorocarbon. Why is it a solid? It's huge. We're looking at orders of 400 or 500 of these that are all then linked to each other. So that's why we can pick up that solid, is we've made it now so massive that we've increased the amount of very weak forces. Okay? So that's kind of our overview of our alkyl halides. What we're now going to kind of, well, almost. We want to evaluate our nomenclature. I'm not going to talk too much about nomenclature. Really the only thing that's new for our alkyl halides, as far as we're concerned right now, would be that purple box on the right. Okay? You should be fairly confident with your alkane nomenclature. All we're now doing is adding a halogen into that process, and we have to specify that halogen now as a substituent on our main chain. Okay? So we'll have to specify where it's located on the main chain using our numbers, just like we would with our alkyl groups. So we could use our methyl or propyl or ethyl or all that fun stuff as well. Okay? So if you have fluorine, we then refer to it as fluoro. Okay? So that's the substituent is fluoro. Okay? If we have chlorine, chloro, bromine, bromo, iodo, or iodine. Okay? That's the standard way to go through and name these. Okay? That's your IUPAC nomenclature. That will be the one that you're most responsible for. However, you will see another version show up. Okay? If we take a look at our priority list here, you'll notice our alkanes are a higher priority than our halides, which is why we name our halides as a substituent with our chloro, fluoro, bromos, and all that fun stuff. Okay? But what if our alkane is really, really tiny? Let's say a methyl group. Okay, so just a single carbon. So I don't have a whole lot of space to draw here, but let's go lower left-hand corner. If I look at this compound, what's our IUPAC name for this so far? Fluoromethane. Our fluoro is a substituent on that carbon chain of just being one, so we could call that fluoromethane. Depending on the reactivity of this compound, or what I might want to accent when I'm talking about its chemistry, I might change my naming on that. Because really what I'm concerned about is that that halogen is actually driving the chemistry around this compound. So instead of calling it fluoromethane, I want to accent the fact that the fluoride is really important. So what I might refer to this as is fluoride is my primary chain. Well, what's the substituent on the fluoride? A methyl. So the other name I could use would be methyl fluoride. Okay? How do we decide which one to use when? It's nomenclature. Good luck. Okay? You're responsible for the IUPAC name. Realize that you may see that other version, your common name, where we're saying the halogen is our primary substituent on that. And then the alkyl group our halogen is our primary chain, if you will, and then the carbon chain is a substituent on that. So we would name it for the halogen or halide with the carbon chain being attached to it as an alkyl halide. Huh, interesting. What do we call this functional group? Alkyl halides. So we actually named the functional group in a common method as opposed to the IUPAC method. If we were going to refer to our functional group in an IUPAC method, what would we call it? A haloalkane. Okay, kind of get the idea? So let's take a look at a couple examples. And I'm horrible at nomenclature, so hopefully I don't botch these, but let's see what happens. Okay, let's take a look at the left one. What's our first step when dealing with nomenclature? Find the longest carbon chain. Where's our longest carbon chain? 3 carbons. Where's our 3 carbons start? Depends on how we're going to start it, so let's decide how we're going to start it. We'll probably start at the chloro because it's number 1. It has nothing to do with electronegativity. It has to do with the numbering. Okay, so the numbering, if we start at the chlorocarbon, that carbon gets the assignment of 1, and we'd have 1, 2 as far as our substituent count. Okay, as opposed to if we numbered it the other direction, it would be 2, 3. So we want our lowest possible numbers. Okay, so we can go up to identify our next carbon. Where's our last carbon? Dang it. I was hoping for you to tell me it was. Everybody say, oh, it's the one going down. And I was going to circle up and say you were wrong. But it doesn't matter. Why does it not matter? It's going to get us the exact same carbon chain, the exact same name, so it doesn't matter. Okay? How many carbons do we have in our main chain? 3. So we could refer to this as propane. Why'd you make it an ane ending? It's an alkane. Okay, what are the substituents on our alkane? We have our chloro and a methyl. And our methyl. Where's the chloro located? Carbon number 1. Where's our methyl located? Carbon number 2. How do we put it all together? 1 chloro, 2 methyl propane. Why? We go alphabetical. Chloro with a C goes before methyl with an M. Okay, so we end up with the name 1 chloro, 2 methyl propane. You'll notice I won't write that out because I'm lazy. Sorry. And also on any kind of test, this is exactly how I would identify it and then look at my multiple choice answers and hope they didn't give me the opposite because I am that bad at nomenclature. Okay? How about the next one? Or should I let you guys try and do that one on your own first?
Just try it.
Okay. You got questions about the nomenclature?
No.
Find our main chain. Where's our main chain going to be in this case? It's going to be the ring is what we would circle. Okay, so let's name our main chain first. We've got a ring, so for sure has to be a cyclo. How many carbons are in our ring? 5, so we have pent. And then an ane because it's all single bonds. Okay, what are our substituents? We have an ethyl and fluoro. I don't know why I decided to capitalize fluoro, just in case you asked that. Where are those substituents located? Good. Which one's 1?
No, it's fluoro.
Why is it fluoro?
We're in chapter 7 right now, so obviously.
Is it higher priority? If we go back to that priority slide, alkanes are actually higher priority than halogens. How do we decide which one comes first? It's alphabetical. When you hit a ring, it goes alphabetical with 2 substituents. When you hit 3 substituents, the rule changes and it becomes lowest number. The lowest number for the substituents. Okay. Let me caveat this. I'm like 95% certain on that, so I could be wrong. Right. Remember, I'm not going to lie. When it comes to nomenclature, it is my weakest subject because it's a rule. You just have to know the rule. And I'm horrible at memorizing things. So it should be 1 ethyl, 2 fluoro, cyclopentane. Which one shows up first, the 1 ethyl or the 2 fluoro when we write out our name? The ethyl, and that's because that's alphabetical. Okay, so the ordering in front when we put our substituents out there is alphabetical. When it comes to our cycloalkanes, between a halogen and an alkyl substituent, we number based on alphabet as well, okay, with 2 substituents. As soon as we add a third, we want a number to get us the lowest possible sequence. I think I'm going to regret putting on a substituent here, but let's see if I can do it. Okay, yeah, I am going to regret this already, I can tell you. As far as numbering, which gets our lowest number? The methyl, the fluoro, or the ethyl? So we want the lowest number, so it can't be the methyl. Because if we make it the methyl, then our fluoro and ethyl are going to be much higher numbers. So number 1 has to be our fluoro or ethyl. Depending on which way we number it, do we get a different numbering? If we started with the fluoro as carbon number 1, what would be carbon number 2? The ethyl. If we started with ethyl as number 1, which would be carbon or atom number 2? The fluoropentane. position. So we would end up with 1, 2, 4 for our substituent numbers. Either way we numbered it. How do you decide in that case which one gets the lowest number? I think that goes back to alphabetical. Okay.
I think you said if it was 3 or more, it's correct.
So if it's 3 or more, we go with the lowest number. But then what's the issue with this structure? So our lowest number has to put our fluoro and ethyl as number 1. We cannot put the methyl as number 1. So that's our rule there. But then the issue is when we get up to trying to number our fluoro versus our ethyl, we get the same numbering system. There has to be one answer when you go through and do your nomenclature. And I think that's when it switches back to, you'd end up with too high numbers on your fluoro and ethyl. So we would end up with either 1, 2, 4 or 1, 3, 4. 1, 3, 4 gives us a higher number than the...
But wouldn't the ethyl group take priority over the methyl? So that is
So, and that's where nomenclature hits weird rules, especially with your halides and your alkane groups, is that their priorities are virtually identical. So we have to come up with another rule to separate the two of them, and I'm pretty sure that rule is lowest number alphabetical. So it'll go alphabetical with 2 substituents. As soon as you hit 3 substituents, it's lowest number. If the lowest number doesn't solve it, you go back to alphabetical.
unless we had like a
one
purple
would be
group or blue.
Alphabetical. That's all alkanes. That's all alkanes is what you just listed. Okay. As soon as you move to a different functional group, say a ketone or something else, the ketone for sure takes priority. Okay. So between your halides and your alkanes, there is really no priority difference. So to come up with that numbering, it's got to be alphabetical, lowest number, alphabetical. Okay. I will try my best to not give you some curveball nomenclature one with cycloalkanes. And I'm pretty sure the ACS doesn't either. Okay.
So we use 1 ethyl, 2 fluoro, 4 methyl.
For this structure, I would run with, yes, 1 ethyl, 2 fluoro, 4 methyl, cyclopentane. Okay? I know, everybody loves nomenclature. You had to ask for a difficult example. I tried to make it easy and give you simple examples. Okay? Questions about the nomenclature? Okay. Your homework 15, I think, gives you 3 practice questions with alkyl halide nomenclature. Your textbook will give you a whole bunch of other examples. Okay?
How much of that should be accepted in the test?
As far as percent-wise, on exam 3, no more than 10%, because that's the A-B fail line pretty much. Okay? So if you decide to completely ignore nomenclature, I still want to give you the option to be able to get an A, okay, by knowing everything else. When it comes to the ACS test, they directly test on nomenclature in some problems, and then they will indirectly test using nomenclature as well, because they'll say, what's the reaction between hydrobromic acid and 2-chloropropane? Well, if you don't know how to draw the structure of 2-chloropropane, you're not getting the answer. Okay, so you still do need to be familiar with your nomenclature. In most cases, they're sticking with really simple structures and really simple names. You should be able to get those structures pretty quickly and easily. Okay? Reactivity with our alkyl halides, okay, which is what we were already starting to talk about. Hey, remember those electron energy diagrams we were talking about? The different shading? Guess what we've got? There it is. There it is. That's what I'm talking about. When we look at the shading on our alkyl halides, what we're saying is that there's a lot of electron density around the halogen. So it gets the red shading color, suggesting that we've got a lot of electron density there. What happens on the carbon end? Well, all of that electron density has been sucked away to the halogen, which means it needs to become positive. So they start drawing it as the shading of the blue color. Okay? So there's a variety of ways you can see this with this shading process, but if we can't give you colored exams, I guess we could give you colored exams, but it's too expensive. You might see that electron density shifts in a different fashion. So we've got a whole bunch of different options here, so let me draw it out a little bit bigger. We could go through and say, as we've been doing, a partial negative on our chlorine and a partial positive on our carbon. you'll notice that I'll circle the charges. Those don't always get circled. Okay, we could also go through and show where the electron density is shifting to and get kind of more of that curved arrow kind of dynamic with it, showing where the electrons are moving. Okay, what we'll do is show the electrons are moving towards the chlorine. And in the process of doing that, the carbon becomes positively charged because the electron density is shifted that way. So that dipole arrow is just trying to show where the electron density is moving. Okay? Kind of makes sense? We said this really contributes to our intermolecular forces and increasing the melting points and boiling points over our alkanes. And this is also what's contributing to our reactivity. With that carbon becoming partially positive, we could potentially share electron density with it, which means that carbon could act as an electrophile. So what would need to react with that electrophile? A nucleophile, not an electrophile. Is that what someone was about to say? Not hydrogen. What's a characteristic of a nucleophile? It should have extra electron density, so what we would expect to see on our nucleophile would be lone pairs, even a pi bond potentially. Pi bonds are a little bit more or less reactive, but we could work with pi bonds. And we could also see a straight up negative charge. Okay. So if we're going to try and see how an alkyl halide reacts, what we would expect to find in the nucleophile is something that matches one of those definitions: lone pairs, pi bonds, or a negative charge. Yeah?
When you're talking about something reacting with the carbon here, are you talking about it replacing the chlorine?
Didn't get that far, but yes.
Okay, but earlier we were saying that the chlorine couldn't be a base because it can't have more than one bond. But if it's getting replaced, then
Chlorine, so what we'll show that reaction. I think it's actually the next slide. It's not quite the next slide. Well, actually it is. What's going to happen is the chlorine's not going to gain another bond, but it will accept the electrons of the bond that's already there. Okay, and again, we have to look at the dynamics of that first, but it will not share electrons. If anything, chlorine's going to take electrons, okay, not give them up. So, which brings us to the other side. With the chlorine being partially negative, we could start to think, oh, maybe that could act as a nucleophile, okay, or a Lewis base, share those electrons with something. But it can't have a second bond, which means the electrons on that chlorine, those lone pairs, are not reactive as a nucleophile. They cannot react. Well, why not the bond then? Why can't I take the electrons in this bond to react? Because they're in the bond. Okay? I can't take the electrons directly out of the bond. I'd have to move them from that bond to that atom, the chlorine, first, and then I could potentially do something with it. Okay? So when we look at the reactivity of our alkyl halides, we really only have them acting as an electrophile. The chlorine will not act as an attacker. It won't go out and actually act as a nucleophile. Okay? So our primary reaction that we might look at is the nucleophile reacting with the electrophile. Okay? And what that would start to generate is a substitution. Yeah, we can say that. A substitution reaction. Okay? Before we actually move to the exact next slide, what we want to do is say, does this bond have an effect on the rest of the structure? Okay, and that's a much trickier question to answer. Okay, so what do I mean is if we attach another bond out here to say another carbon, and I'm actually going to add a hydrogen on that carbon for the moment. If we look at the carbon of our alkyl halide, our electrophilic carbon, what does it want? Electrons. So we can get those electrons by having a nucleophile come in and share electrons with it. But is there somewhere else that there are electrons? In the bonds within the structure itself. Those bonds can be broken to get electrons towards that carbon. Why did I go all the way out to that hydrogen? Guess where those electrons come from? From the bond between the hydrogen and the carbon. If we do this, what's the result? Hydrogen breaks off. What happened to the 2 electrons that were between the hydrogen and the carbon? They are now between the 2 carbons. How many electrons are now between our 2 carbons? 4 electrons, which means we have a pi bond. So what we looked at is eliminating a molecule from this structure. Okay, so what we've got in this case is an elimination reaction. If you're having troubles with the eliminations, that's fine. Don't worry. We will talk about this in much greater detail when we get to chapter 8. Okay? Really what I want to get to is that when we look at our alkyl halides, we really only have 2 types of reactions. You'll notice that our conditions are very, very similar. In our first line, what happened? What's the change that occurred? Okay. We have a new bond between the nucleophile and our carbon, which we can see in our product. What else happened? We broke a bond between the leaving group and our carbon. Yes, there's some other things that happen there, and we'll talk about those again in more detail when we get through those. But those are the primary things that happened. We formed a new bond with our nucleophile, and we broke a bond to our leaving group. Why are we concerned primarily about just those 2 and not, say, the new bond that's happening out over here, or, for that matter, the bond breaking in our nucleophile? It's not an alkyl halide. There we go. Remember, organic chemistry, we focus on the functional groups. We're only concerned about the organic molecules. What happened to our organic molecule? Our substrate. We broke a bond and we made a bond. Yes, a bunch of other stuff had to happen at the same time, but I don't care because that's not what I was focused on. Okay? So we have to be kind of careful about what we're referencing when we go through and look at this. There's other reasons why we don't care about it too, and we'll talk about those. What happens in the reaction underneath? Don't answer that yet. What type of reaction occurred for number 1?
Substitution.
We have a substitution. Did I spell that right?
Yeah.
Looks close. We have a substitution reaction. You're going to be responsible for looking at a reaction and saying, yeah, that's substitution. Or no, that's not substitution. You should be able to do that. Is there another reaction that you are already aware of that you should be able to also identify? Acid-base reactions. We now have 2 types of reactions. If I draw out a reaction for you, you should look at it and say, that's an acid-base, that's a substitution, or who knows? Because we're only at 2. We'll get up to 5. Okay? What happens in the next one? What things changed in that next reaction? So the leaving group broke. What else changed? There's a hydrogen that broke off. You'll notice that hydrogen wasn't actually added on there. Why not? We almost always imply hydrogens. If you aren't remembering that we imply hydrogens, you need to draw it on there because they will become extremely important for this type of reaction. What else happened? We formed a hydrogen bond and we formed our pi bond. Okay, what type of reaction happened here? Elimination. Because we eliminated our leaving group and our hydrogen from the molecule, okay, from our alkyl halide. Okay? So now you have the ability to tag 3 different types of reactions: acid-base, substitution, and now our eliminations. In an acid-base reaction, what are you looking for? The transfer of a hydrogen ion, and that needs to be it. If anything else happens also, it's not going to be a strictly acid-base reaction. What happens in a substitution reaction? Something gets replaced. Nothing else changes. We just replace one thing within our structure. What happens with the elimination? We could look at a hydrogen leaving, except what's the issue with a hydrogen leaving? That looks like an acid-base reaction. So we don't want to use that as our identifier for our elimination.
Well, you have an
But a
electron.
substitution does a leaving group too.
It's the electron is taken from the bond and put into a pi bond.
The formation of a pi bond. is our elimination reaction. Okay? So we want to come up with characteristic things to identify. Why? Because each of these reactions or each of these reagents, we need to be able to recall as quickly as we can. Eventually, you're just going to have a list. Probably by the end of this semester, I think we'll probably hit 50 different reagents, okay, which could actually be scaled outwards infinitely, but 50 basic reagents. Okay? You need to be able to decide how each of those reagents is going to react according to which reaction to generate what possible product. You can either memorize 50 upwards of an infinite amount of reagents, or you can have an idea of what's happening within each of the reactions and what can happen or what the results would need to be. Okay? So be familiar with the individual types of reactions because it's going to help. Okay? Questions about these? And let me clarify that. Questions about the substitution one, not the elimination one. We'll deal with that in Chapter 8. Yes?
Not even about that, but you said there's
Okay.
5 total?
5 total.
We just did 3 5.
You want me to list them all off? Acid-base, substitution, elimination, addition, radical. So the addition and the radical, you will see the radical. I'm planning on doing that one the Wednesday before your exam, so you'll have time to practice that one. And then the addition is after exam 3. It's another 3 or 4 weeks. For alkyl halides, we only have 2 types of reactions, substitution and elimination. They're a nice functional group because those are the only 2 types we have. If we moved up to alcohols, most people tend to hate alcohols. What types of reactions do we have for alcohols? Everything except addition reactions. Okay, what do you think an addition reaction might be? You have to add something to a structure. How are you going to add something to the structure? If you took something away, it'd be a substitution. What did we do in the elimination reaction? We removed a molecule. What are we going to do in an addition? Add a molecule. What do you think the reagent's going to be for adding a molecule? Something with a pi bond. Okay, so it would be the opposite of an elimination. So we can still find these patterns again. We're trying to look for these, identify them, and remember them. Okay? So, basic elements of our substitution. So we've got the reaction highlighted up again. You'll notice that I included a bunch of kind of weird symbols. Lg isn't an element, and it doesn't even fit our halogen rules or any of those classifications. The nuke at least makes sense because what we're looking at for the nuke is nucleophiles. That's something we've already talked about. And then solvent, written in green, is exactly what we say it is. It's the solvent. Okay? You'll notice with the nucleophile that I have an M/H. What does that mean? The M means metal. What is the H? Hydrogen. So our nucleophile can sometimes show up being bound to a metal, or it can be bound to a hydrogen. Is that going to change the reactivity of the nucleophile? Let's take a look at an example. Metal. Good classic metal that we end up using would be sodium. We'll put that next to OCH3 versus H, OCH3. What's our nucleophilic atom? Why the oxygen? Because it has implied lone pairs, so that should help us. Which of those oxygens is more nucleophilic? You're cheating, we already talked about it. What type of bond is there between the oxygen and the carbon? Polar covalent bonds. Do we care about that bond? Why not? It's the same in both. Find the difference. What's the difference? Oxygen to sodium versus oxygen to hydrogen. Yes, sodium has such a lower electronegativity that what type of bond is there between oxygen and sodium?
Oh, it's ionic.
It's an ionic bond, which means really when we write that out, we're not looking at sodium being bound to oxygen. We're looking at oxygen negative and sodium positive. What happens when we look at the oxygen bound to hydrogen? Don't tell me that. That's a force.
That's a force. Yeah.
What's the bond between oxygen and hydrogen? It's polar covalent. Okay, if it's a polar covalent bond, we don't generate the full-on charge of positive and negative. Which of these two species is going to generate the stronger nucleophile? The sodium one, the one with the metal. So if we see a metal showing up on our nucleophile, we're looking at a strong nucleophile. If we see a hydrogen showing up on our nucleophile, we're looking at a weak nucleophile, okay, or at least weaker. So it's going back to those same basics. Everybody goes, oh, polar covalent, we didn't need to know that. How did we decide what our nucleophile was? It was going back to what is the bond. How did we determine what the type of bond was? Differences in electronegativity. So if we understand what's happening with our electronegativity, all we have to do is apply it again, and again, and again, and again. Okay? And that's going to help us get through this without having to strictly have everything memorized. Okay? So let's go through and look at the pieces. Your substrate, I did try and color code this, it may not be obvious. Your substrate is in blue. That's going to contain the electrophilic carbon, so our reactive carbon. So this whole piece is your substrate. You'll notice that on the reactant side, our substrate also contains the leaving group. And on the product side, our substrate contains the nucleophile, or has the nucleophile attached to it. So what we're really concerned about with our substrate is our electrophilic carbon. So whatever group or whatever piece has that electrophilic carbon is our substrate. Okay? When dealing with the alkyl halides, you'll almost always see that our substrate, our electrophilic carbon, is shown as a strict reactant. Okay, so it's the very first thing that we see. Does it have to be placed there? No, it could be placed above the arrow. Okay, it's still technically a reactant above the arrow, but we may be trying to emphasize a different form of reactivity, and that's why we change it in that different spot. It's still a substitution reaction. It's still an electrophile. Okay? The leaving group. So LG is standing for leaving group. Why might it be called a leaving group? Okay, what's our characteristic of our leaving group, particularly in this chapter? It's our halogen, and what do our halogens do? Take electrons from carbon. Why would they take electrons from carbon? They're more electronegative than carbon. Electronegativity plays a really important role. So in the course of this reaction, that leaving group has to take the electrons away from our carbon. Because it is taking the electrons, it now leaves the structure. Okay, so our leaving group will always take electrons with it. If we take a look at the nucleophile, we already talked about that. That is going to be the species that's going to donate electrons to our substrate. So remember, as our leaving group leaves, it's taking the electron density, leaving that carbon what charge? Positively charged. How do we stabilize a positive? With electrons. Do we have a negatively charged species in a nucleophile? Yep. So how could we predict what this reaction is going to happen? We find the biggest negative and we find the biggest positive, and what do? Put them together. Okay? The solvent's going to be there to kind of facilitate or potentially harm the reaction. Okay? We will always look at it as facilitating the reaction, because what are we trying to do when we get into lab? Get out of lab. Okay? So the solvent that we're going to choose is going to do its best to help the reaction along so we can get out faster. Okay? The Hertz is showing up there because when we look at the individual mechanisms and how the solvent can affect the reaction, it turns out that certain solvents will hurt a particular mechanism and prevent it from functioning, which would mean what about that solvent choice? Don't pick it. Okay? You'll notice there's some other summaries coming along with this. With your substrate structure, we've got a couple different classifications. We've talked about all of these to varying extents. We've got our zeroary, primary, secondary, tertiary, and if our carbon happens to be sp2 hybridized. In this chapter, do you think we'd particularly talk about sp2 hybridization?
No.
Why not?
It's not alkanes.
That's not an alkane. Your alkanes are all sp3 hybridized. The sp2 will show up because what we're going to also start to do is talk about substitution as a whole, all substitution reactions. So we will look at the reactivity of alkenes a little bit as alkene halides. Okay, so we will evaluate those. Within the leaving groups, we're typically using two common ones, bromine and chlorine. Okay, we can use iodine. Fluorine is never or very rarely ever used. Why? Fluorine is incredibly small so that when it leaves and takes the electrons, we have effectively a point charge. What's the issue with a point charge? We can't distribute that electron density around over a large enough area, and it becomes very, very reactive. So it goes immediately right back. Okay? So our primary focus is, again, bromine and chlorine. We can see iodine pop up as a good leaving group as well. Okay? What? Iodine, yeah. When we look at the nucleophiles, you'll notice I'm bringing in some extra notations here, which will make a little bit more sense probably on Monday. If we look at our nucleophile and it's bound to a hydrogen, we're looking at an SN1 mechanism. If we look at our nucleophile and it's bound to a metal, we're looking at an SN2 mechanism. Okay? Any ideas why? What did we say happened to the nucleophile if it was bound to a metal? It was strong. What do you think is really important in an SN2 reaction? We need a strong nucleophile. Okay? When we move to the solvent choice, we can go through and classify solvents according to their particular characteristics, which we might talk about today in the short time we've got left. In an SN1 type reaction, we'll look at a protic solvent, and in SN2, we'll look at a polar aprotic solvent. Okay, again, we'll talk about those definitions here in just a little bit. Okay. Our substrate classifications, everybody remember zeroary, primary, secondary, tertiary? Everybody okay with that? Okay. The one extra one that we'll tag on here is we could go through and look at an sp2. So if we drew on, say, a benzene ring and put a chlorine there, that carbon, where our chlorine is bound, okay, zeroary, primary, secondary, tertiary is really only based around our singly bonded carbons, or sigma bonds. Okay? So we could go through and say, well, that carbon has two carbons bound to it, so it's secondary, except the secondary classification only works if they're all single bonds. Are they all single bonds around that carbon? Nope, there's a pi bond. So we can't really use our primary, secondary, tertiary classification. What instead we'll bring in is some more information about what that structure is. And because it's not on the slide, let's shift that up a little bit. We're looking at an sp2. Okay, so we're going to start to reference its hybridization. Okay, just to be consistent with that. Hopefully the rest of those you remember and you can read through and not too concerned about that. Questions, actually, before I skip that?
Yeah. So we're not going to reference how many carbons are attached to the carbon, just what its hybridization is?
For the sp2, yes. That's all we're going to reference. Okay, we're going to refer to the hybridization. For our zero primary, secondary, tertiary, that's in referencing how many carbons are attached, and that will become a really important classification. Leaving group ability. So we've got a new structure here. Which of those leaving groups is the worst? Most people are actually able to pick this up without really any chemistry, without too much chemistry. So we're all concerned about that carbon, and I want to know which of those leaving groups, so which atom would be the absolute worst leaving group? Why would the hydrogen be the worst? If it's going to act as a leaving group, let's add a curved arrow. What would happen? The electrons are going to move to that hydrogen, and we would have H with 2 electrons being negatively charged, also known as, this is a good hint on its stability. Very few of you actually picked up its name. It's hydride, can actually form. Why do you not know its name? It's incredibly unstable. What do we need to happen with our leaving group? It had better be stable. Which leaving group is the absolute worst? Hydrogen. Why is hydrogen a horrible leaving group? Can't distribute the electron density because It's tiny. What else? What's its electronegativiity? It's one of the lowest electronegativities. As far as organic chemistry goes, it is the lowest. Hydrogen's not going to be very good at stabilizing that electron density. If it can't stabilize the electron density, it's a horrible leaving group. Okay? So hydrogen's are worst. Between the others, which one do you think is the best?
Bromine.
Why bromine?
Largest.
It is the biggest. Okay? So what we'd ultimately end up doing in this comparison is looking at each of those as a leaving group and trying to decide something about its reactivity. Okay? For our leaving group to actually leave the structure, it must leave as a stable piece. Hydride is incredibly unstable. How stable is hydroxide? Not very stable. It's a strong base. That doesn't work. How stable is chloride? Hopefully we won't get too much of this after the final exam. Okay? If you go home and cry, which will happen, it is organic chemistry, it's just a feature of it. Okay? You are streaming chloride ions down your face. Okay? It may sting a little bit, and as long as you're not in public, it's probably not that big of a deal. Okay? Bromide ion. Okay? Even more stable than the chloride because it's bigger. What's another pattern that we could notice within these? So we could look at size. We could also look at reactivity. How are each of these reacting? As a base. Which of those is the weakest base? Bromide. Bromide is the weakest base in that list. Okay, why is it the weakest base? We could look at its conjugate acid being very strong. We could also look at it being very large. It stabilizes the negative charge. We go back to those same rules. Okay? So for a good leaving group, what we're hoping for is that it stabilizes the negative charge as best as it can. The common traits that we would find for these, they are typically electron withdrawing, meaning they're very electronegative. They're also usually weak bases once they've left. Okay, they can't act as a base until they've left. Why?
Because they can't have multiple bonds.
They can't have the multiple bonds, particularly when we're looking at our halogens. And then they're typically also polarizable. Polarizable is just a fancy way of saying they're really big. Okay? So we've got a bunch of leaving groups listed in this table, which did come from your textbook, so it's listing off good leaving groups and also bad leaving groups. One thing I do want to point out here, you'll notice one of the good leaving groups is water. How could I get water as a leaving group?
The hydrogen and the hydroxide.
Why would that become a good leaving group? What charge does the oxygen become? Try again. Formal charge on the oxygen right now.
Right.
Nope, right now.
Oh, it's +1.
It is not partial, it is not neutral, it is formally positively charged. Does an oxygen want to be positively charged? Nope, so what does it do? It steals electrons. Ta-da! And it leaves the structure. Okay. So we're looking at an electron withdrawing group, and we want to minimize that charge. Water is an awesome leaving group because what happens to the charge on our leaving group? There isn't one. That's a good leaving group. Okay? Yeah, we're over time. Sorry.